Question 2, so we are decomposing group 1 nitrate. So group 1 cations M+, because ground metal likes to lose 1 electrons, therefore they'll have a +1 cationic charge. Then you have the nitrate, which is NO3-. The +1 and the -1 charge cancel out, so you get MNO3, and this is an ionic compound, and compounds are uncharged. The overall compound is uncharged, although you contain ions, and ions are charged, so you need to be very careful. When they decompose, they give off a gas. The gas relights a glowing splint. Name the gas very clearly. This is oxygen, because oxygen support combustion. Oxygen relights a glowing splint. A burning splint was the one where the fire is still going. A glowing splint is when the fire has been put out, but you still have a little bit of those flicker of flames that, in the presence of oxygen, it's going to burst to give you the fire again. So it's going to rekindle, or it's going to relight a glowing splint, and oxygen does that. So a student investigates the rate of decomposition of 4 group 1 nitrate. So heat each of the nitrates separately with a Bunsen burner. We use a Bunsen burner in the lab. You measure what is the time taken for a glowing splint to relight for each nitrate. Okay, so the easier it is to decompose, the faster you will get the oxygen, and therefore the faster it will be for the glowing splint to relight. So the slower it is for the glowing splint to relight means the oxygen is produced much later on, so the rate of reaction is slower because it's much harder to decompose the group 1 nitrate. All right, so we have a source of heat here, and we have to control the amount of heat supplied. How can we keep the heat supply constant? So the heat comes from the Bunsen burner, and I hope you know in a Bunsen burner you have a hole, you have gas tap or valve. The one where you turn around to adjust the amount of gas that goes into that comes out from the Bunsen burner. So that will adjust the volume of the gas that comes out at that particular moment, and of course what else? The distance as well. So if you heat from this distance, and then suddenly the next two you heat from a higher distance, then the heat is not going to be the same. All right, so you want to keep the heat supply constant. So this is just suggestion. If you're doing this in the lab, these are the things you should be looking out for. All right, so keep the valve, we want to keep the fire intensity the same. All right, so keep the flame intensity, not the fire intensity, because it's the blue flame that we want for heating, right? Not the yellow flame. So keep the flame intensity constant by not changing the gas, by not changing the gas type, by not changing the A-hole size at all. So you do not want to adjust, make a little bit more oxygen or a little bit less oxygen. You just leave it the same for all the experiments. And then also turn the gas tap or valve by the same amount. You don't want some experiments to have a large amount of gas be given out, and therefore you get stronger flame or whatnot, right? Okay, the other one, of course, is what you could think about is keep the distance between, not the flask, this is a tube, this is a boiling tube, and heat source. You want to keep that distance constant. Okay, so that could be a third alternative for keeping the heat intensity constant, is that this distance must be kept constant as well. So you don't want to make it too high or too low across the different experiments. Suggest a variable involving, so this one must involve the metal nitrate. There should be control. So of course, if we have a lot of metal nitrate to decompose, it's going to take a longer time to decompose. If you have a lot of the metal nitrate, then potentially there are two things that can happen. If you get more metal nitrate, you could get more oxygen being given out, but your experiment is just as soon as some of the metal nitrate decomposes and give off some oxygen, then you could get the glowing spleen being relighted. Okay, so really I am reluctant to say use the same amount. I'll probably go for surface area, which is one of the easiest thing to think about, because if I use some metal nitrate that are powdered and I use other very crystalline, you know how crystals form, they tend to be a little bit less powdered because crystals are bigger form of a solid, right, rather than a powdered form. They actually clump together to give you very nice crystals. So crystals will have a different surface area to the powdered form compared to something which is lumpy as well. So you can get lumpy, they come in big lump, they come in powdered, or you crush them, or they can be in very crystalline form. So different surface area. Okay, so I'll be thinking about the surface area of the metal nitrate used. So at least that's to do with the solid inside and not to do with the source of the heat, which was in the previous part of the question. So these are three experiments for the 4 different group 1 nitrates. So lithium nitrate, it's important that you can do formula easily. Rubidium, I suppose you probably don't know the formula for rubidium that well, but lithium, potassium and sodium, first 20 elements as stated in the theory syllabus. Use the times in the table to calculate an average time. Do not use any anomalous time. Anomalous mean out of ordinary. Okay, so typically out of ordinary would mean that they are typically wrong results. Okay, so if you compare these 3 different experiments, 100, 150, 100, this is anomalies. Okay, this is clearly very different from the other 2. 150, 300, 320, this is very clearly anomalous for this one. 400, 450, 410, they are quite close. At least they are not like a difference of 50 apart. Well, actually this and this are closer. This is not very close, so perhaps I don't want this. I would use average this and this because they are so much closer. Okay, between the lowest and the highest the difference is 50, just like the lowest and the highest the difference is 50. And the next one, 200, 200 and 240. Seems like the 240 is anomalous, so I can cross that out. So to get this, I will get 100 plus 100, but it will be average over 2 experiments because I cross out the result for 1 experiment. So it's 100 plus 100, use bracket, so I'll get 100. 300 plus 320, so you can use your calculator for this obviously, and you get 310. 400 plus 410. So we cross out anomalies or anomalous results, or what we call anomaly, okay, easily in order to prevent any unwanted results. Not prevent unwanted results, to prevent any inconsistency in experiments which clearly are a result of certain errors, and therefore you don't use them because they will affect the accuracy of your result. That's why we repeated experiments in order to get consistent results. They are concordant. Okay, just like in titration you would do until you get concordant titers. Here we'll get concordant results. Our results are time, so these are concordant. This is an anomaly. It's not concordant with the other results. Which metal nitrate decomposes the fastest? The fastest, and then you have to use information from the table to explain your answer. Okay, in a theory paper, sometimes they don't give you lines like this. That's why it's important to label, so that you're answering and addressing every single part of the question. The fastest reaction would take the shortest time for the glowing spleen to relight because the oxygen is produced the fastest. That's why it takes very little time for you to get the oxygen, and therefore it takes very little time for the glowing spleen to relight. So there has to be lithium nitrate there. So which metal nitrate? So just write the name, very straightforward. And the explanation is that, well, as I mentioned, it takes the shortest time, and we have just calculated the average was 100 minutes or 100 seconds. These are second, okay, because the unit was given there. So 100 second out of the 4 averages for splint to relight. Alright,